So for today's discussion, we'll be doing section 1.7. Actually, this is not 1.7. This should have been section 2.1. So section 2.1, it's relative extrema and second derivative test. So I assume that you've watched the associated lecture video. If not, please go to that first before before reviewing this session here. But anyway, let's have a quick recall of what the lecture contains. So first, we recall the definition of relative minimum and relative maximum. So here we have a function of two variables, f of x, y. We say that this function has a relative minimum at the point AB if f of a comma b is less than or equal to f of x comma y for all x comma y on some disk centered at the point AB. And then we say that this function f of x comma y has a relative maximum at AB if f of a comma b is greater than or equal to f of x comma y for all x comma y on some disks centered at the point AB. So with this definition, of course, we assume that the point AB, it's in the domain of your function f, since you are evaluating your function f at the point a comma b. Okay? Now, if the above inequality, this inequality here or this inequality here, holds for all x comma y in the domain of f, so for the full domain of f, then we say f has an absolute minimum. So that's for this, or absolute maximum, that's for this guy at the point AB. So here is a beautiful sketch, a beautiful graph of this function here. So suppose this part here continues to be flat. So in here, we have a local maximum here. We have a local maximum here. Here, we have a local maximum. And at the same time, we have an absolute maximum. In here, we have a local minimum. And at the same time, an absolute minimum. Okay? So this is a graph of some function with local minimum or local maximum or absolute maximum, absolute minimum. By the way, when we say local, it means relative. Okay. We also recall the term critical point or stationary point. So the point A comma B is a critical point or stationary point of your function f of x comma y if either the gradient of f evaluated at a comma b is equal to the zero vector. Remember, gradient of a function, it gives you a vector. So here you have the zero vector. Now, you have a function in two variables. The gradient of that function has components, first partial derivatives. Okay? So this means we have the partial derivative of f with respect to x evaluated at AB is equal to 0 and partial derivative of f with respect to y evaluated at AB equals 0. Okay, so take note of that word and. Okay. Or we have the following. One of f of x, one of f sub x at AB or f sub y at AB does not exist. So there's a possibility that the partial derivative at that particular point AB won't exist. Okay. In here, of course, we will assume again that AB is in the domain of F. Okay, in the domain of F. Now, we recall one of the two important theorems that were discussed in that lecture video. if f of x comma y has a relative extremum at AB, so it means that either the function has a relative minimum or relative maximum. Okay? So if the function f has a relative extremum at AB, then the point AB is a critical point um, of f of x, y. So we have here f here. Okay? So it's a critical point of f of x, y. So let me just edit this part. This is f of x comma y. And in fact, if you get the gradient of f, okay, gradient of f at the point a comma b, you should get the zero vector. Okay, so this is our implication. F has a relative extremum at AB, then you have the gradient of f at AB that's equal to 0. Okay? Now, let me remind you that the converse is not true. Okay? If the gradient of f at AB is equal to 0, it does not mean that f will have a relative extremum at the point AB. Okay? So you have gradient of f at AB equals 0, then the function may or may not have a relative extremum at AB. So this is this remark here. The converse of this statement is not true. Okay? So again, this guy here, this is f of x comma y. And then the second theorem, which we're going to use, is the second derivative test. Okay? So very much similar to the second derivative test and the function of one variable. But of course, this guy here involves partial derivatives. Okay? So let us state this second derivative test for functions in two variables. So suppose AB is a critical point of the function f, with second order partial derivatives of f continuous on some region containing AB. Okay? And then we define this capital D by second, so let me just read this as f sub xx at AB times f sub yy at AB minus f of x sub y, sorry, f sub xy at AB quantity squared. Okay? So again, define D to be f sub xx at AB times f sub yy at AB minus f sub xy at AB squared. Okay? Then, f has a relative minimum at AB. Okay? Relative minimum at AB if your capital D is greater than 0. And your f sub xx is also positive. F has a relative maximum at AB if capital D is positive and f sub xx is negative. Okay? So again, relative minimum at AB if D is positive and f sub xx is positive. And then relative maximum at AB if D is positive and f sub xx is negative. Okay? Now, we say that f has a saddle point at AB if your D is less than 0. So it does not matter whether we don't care about the sign of f sub xx if your D is negative. Okay? Now, look at this. You have your D positive, you have your D negative here, and we don't have d equals 0. In fact, if d is equal to 0, okay, if d is equal to 0, then we cannot conclude anything. Okay, so let me just write it here. If d equals 0, no conclusion. Okay, so let's have our first example for this discussion. Find and classify all critical points of f of x comma y equals 4 plus x cubed plus y cubed minus 3xy. So find and classify all critical points of f of xy equals 4 plus x cubed plus y cubed minus 3xy. So, of course, we will start by finding the gradient of f. Okay, so we will need this. And this gradient, again, this is just f sub x, x comma y, comma f sub y, x comma y. Okay, and then we will need the points x comma y such that this vector here is the 0 vector. Okay, so basically we equate this guy here to 0, we also equate this guy here to 0, and then we just solve. We need both of them to be 0. So we will have to find those points x comma y such that both of them are 0 after evaluation. So we solve this system. Okay, f sub x xy equals 0 and f sub y xy equals 0. So if we try to solve this, we will have the following. So you will have 3x squared minus 3y equals 0. Then the other one is 3y squared minus 3x equals 0. Okay? Then of course, you can factor out the 3, it's never 0. What you will have here is x squared minus y equals 0 for the first part here. So this guy here, you will have y equals x squared. And then for this second part here, you will get x equals y squared. And then you can, you can now either substitute y equals x squared into this or x equals y squared into this, and then you'll be able to solve for the system. Okay? So if you do that, the solutions that you will get, anyway, so let us look at that. So you will have y equals x squared, okay? But x is equal to y squared. So you will have y squared squared, and this is equal to y to the 4. So you will have y to the 4 minus y equals 0. And then you can factor out y. You will have y cubed minus 1 equals 0. And then you can further factor y cubed minus 1 into y minus 1 times y squared plus y plus 1 equals 0. And this guy here, this will never be 0. So what you will get from here is that y equals 0 or y minus 1 equals 0. And this y minus 1 equals 0, it means y equals 1. And therefore, you have y equals 0 and y equals 1. All you need to do is to substitute to this to any of this equation here. Okay, and then you will end up with the following solutions. So you will have 0, 0, and 1, 1. So this means these are critical points. This guy here and this guy here. These are critical points. And then we want to classify these critical points in the sense of being relative minimum or relative maximum, or maybe saddle point, or maybe just an ordinary point. Okay? So we try to find the second derivative tests. Okay? I mean, we need to use the second derivative test. So we need to find the second derivatives. So f sub xx, okay? So this is your f sub x, okay? So if you get the derivative of this with respect to y, you'll just, with respect to x, you'll just get 6x, okay? And then this is your f sub y. If you get the derivative of this with respect to y, you'll get fyy. And this is 6y. Okay? And if you get, for example, in here, you have your f sub x, you get f sub x y. So the derivative of this with respect to y, you just get -3. And observe, if you used this, okay, if you use your f sub y, you get the derivative of this with respect to x, okay? You have your f yx. This will give you -3 also. And it is expected, okay? It is expected. Take note that this is a very nice function. And for those nice functions, your f sub xy, it's the same as your f sub yx. Okay? So that's why in our formula for your d, for the formula for the d, you have f sub xx, f sub yy minus f sub xy quantity squared. This guy here, it's actually roughly decomposed as f sub xy times f sub yx. Okay? So that's why we only have this guy here. Okay? So you have this. Okay? And from here, we can evaluate at 0, 0, and then at 1, 1. Okay? And then we can solve for the d. Okay? This d here. So let's put that in a table. So you have the point 0, 0, you have the point 1, 1, you have your f sub xx, f sub yy, and then f sub xy. And then your d here. So at 0, 0, f sub xx, this is equal to 0. Here, f sub yy, this is also 0. F sub xy, it's equal to -3. Okay? So we have that 0, 0, and then -3. And therefore, d, that's equal to -9. Okay? So your d here, this is negative. According to the second derivative test, this function will have a saddle point at this 0, 0. Okay? So we have a saddle point. On the other hand, if you have the point 1, 1, if you have the point 1, 1, f sub xx, that's just 6. F sub yy, that's also 6. And f sub xy, that's -3. So if we calculate for d, we'll get positive 27. Now, your d, it's a positive number. And your f sub xx, it's also positive here. Okay? Which means that at the point 1, comma 1, we have a relative minimum. Okay? So if you look at the sketch of the graph here, we have this. So you have the saddle point somewhere here. This is your 0, 0. And then your 0.11, it's somewhere here. And this is your relative minimum. Okay? So let me try to check using Geogebra. So let us get the graph of this function using Geogebra so we can rotate the graph. Okay? So let me open my Geogebra. So anyway, while I open the Geogebra app, any questions? Okay, so thank you for the response. In here, I now have 3D graphics. So let me just share the screen. So this is GeoGebra, and then let's have fx comma y equals, we have 4 plus x cubed plus y cubed, and then minus 3xy. So this is it. So we will have here, so there's the saddle point. It says 0, comma 0, but the saddle point, yeah. So it's rotating here. So the domain 1, comma, if we look at the top view, okay, if you look at the top view, so you have this point here, 1, comma 1, okay, and then you have this 0, comma 0. Now, the 3-dimensional version, of course, as you can see, the lower point, it's on this. And then the saddle point, it's on this. Okay? So indeed, mathematically, we were able to see that. Okay? All right. So let's go back. This. Now, let's look at our second example here. Let us now consider the function f of x comma y equals x squared y e raised to negative x squared minus y squared. So let us study this function. So what we want to do is to get the critical points, and then we can get, or we identify or classify the critical points. So in here, of course, to find the critical points, we need the first partial derivatives with respect to x and then with respect to y, and then we equate it to 0. So you have these partial derivatives here. This is with respect to x. This is with respect to y. Now, this guy here, whatever your x and y are, they will never be 0. So in here, you will have negative 2xy times x squared minus 1 equal to 0. And then the other guy, you will have x squared times 1 minus 2y squared. This is equal to 0. Okay? As you can see, this is equal to 0, this first guy here, when your x equal to 0 or y equals 0 or x equals, let's write plus or minus 1. On the other hand, the second equation here, this will be equal to 0 when x equal to 0, or when your y equals plus or minus square root of 1 over 2. And as you can see, they will be both 0 at the same time only at x equals 0. Okay? They will be both 0 at the same time when x equals 0. When y equals 0, this guy here will not be 0. Okay? When x equals plus or minus negative 1, this guy here will not be 0. So you must force the other guy to be 0, etc. Okay? So again, these two will be satisfied at the same time if x is equal to 0. Okay? So observe, for all y, 0 comma y is a solution to the system. Your x is equal to 0, so whatever your y is, this is true. Okay? Now, let us try to get the second partial derivatives. So you have your f sub xx. If you try to solve for the derivative of this with respect to x and simplify it, you will end up with this expression. And then here, if you get the derivative with respect to y, you'll just get this expression here. And then if you get the derivative of this guy with respect to y, you'll get this expression here. Okay? And then x equals 0. Okay? If you substitute this 0 comma y, whatever your y is, your f sub yy, that's always 0 because of this. And also your f sub x y will also be 0 because of this. And therefore, if you use the formula for the capital D, you will end up with 0. Okay? And like I said, if your D is equal to 0, we cannot conclude anything. So it could be maximum, it could be minimum, it could be a saddle point, or it could be an ordinary point. So if we look at that graph, or the graph of the function, we have this. Okay? So we have this sketch here, or actually the graph itself. And it seems that at some points we have relative minimum, and then at some points we have relative maximum. So let's check. Or maybe it's just an ordinary line at those points. Okay, this guy here. So maybe let's check again using the using GeoGebra. So we can rotate the sketch, and then we'll actually see what happens on the line or on the plane x equals 0. So in here, we have f of x comma y equals, instead of f, let me replace this as g. So you have x squared y, and then e to d negative x squared minus y squared. So you have this. Oops, it is not obvious, but maybe if we zoom in, zoom out. So in here, I think I can zoom. So as you can see in here, it's starting to show. Okay. X equals 0. What is that? X equals 0. So 0 comma y. So you have this 0 comma y. It means the y-axis. The green axis that you see here, that's your y-axis. So we look at what happens on that y-axis. You have this. It's like, I think it's just an ordinary, at least at this part of the domain, it looks like an ordinary, just an ordinary point. It is not a saddle point. It is not a maximum nor a minimum. Okay. So maybe we can still further. Yeah. So that's the graph. Okay. And of course, if you have the if you look at the bigger picture, it's not really, does not look like what we have on the slide. Looks like flat here because maybe the hills and the troughs, okay, it's low. Okay, just as you can see in here, it looks like the peak, and then the bottom here, it's not really high compared to what we see here in the slide. But anyway, this is your y-axis, okay, and it looks, at each point on the y-axis, it looks like an ordinary point in the domain. So we cannot conclude anything. Okay. Questions? So now remember in function with only one variable, you discuss relative extremum, relative minimum, relative maximum, absolute extrema, also critical points. And there was a theorem there where when you only have one critical point and it is a relative minimum, then it is an absolute minimum. Okay? Also, when you have only one critical point and it is a relative maximum, it is an absolute maximum. Okay? We don't have that counterpart in functions of two variables. Okay? So, well, in functions of one variable also, if your function is continuous on a closed interval, then you can definitely find these absolute extrema, both the absolute minimum and then the absolute maximum. For that, we have a similar similar results for functions in two variables. So we will need our domain to be closed and bounded. Okay, so we'll look into that in this last example. So find the absolute minimum and maximum values of f given by x squared minus 2xy plus 2y on the triangular region D with vertices 0, 0, 4, 0, and 0, 2. So our domain here, it's a triangle with these vertices. Okay, and all the points inside the triangle and also on the sides of the triangle. So we will have a closed and bounded domain. So here, we first find the critical points. So we just look inside this, we use this function, we get the first partial derivatives, and then we equate that to 0, or we equate them to 0. And then we check if the solutions are inside the triangle. So you have here f sub x, that's just 2x minus 2y equals 0. And then f sub y, that's minus 2x plus 2 equals 0. If you solve this system, you'll just get one solution. That's the 0.11. And then this is your region D here. So this is your region D. And as you can see clearly, your 0.11 is inside the region D. Now, in the function of one variable, you also look at the boundaries of your closed interval. So similarly, we do the same thing. We also look at the boundaries of our region. It means you look at this line, you look at this line, and then you look at this line. And then you compare what point or points give the absolute minimum and the absolute maximum values. So let's see. You have the 0.1 comma 1 there, and it's inside your domain D. Great. Next, we consider the boundary of D composed of the 3 line segments. The first line segment, it's this line here from 0, 0 to 4 comma 0. So this is just the line y equals 0. Okay. So basically, this is just your y equals 0 for x inside 0 and 4, or inside the interval 0 comma 4. So as you can see, y equals 0, you substitute that on this line, the maximum value will, you'll get it at x equals 4. Okay. For the second line, you have this. Okay. So line 2, that's your y. Oops, sorry, it's your x equals 0, but your y runs from 0 up to 2. And then you do the same thing. You substitute this inside on the function. Your x equals 0, this disappears, and this one disappears. So you'll just have 2y, and your y runs from 0 comma 2. And then again, you will get which point gives the extremum, either maximum or minimum. Okay. And then the third line is this. Okay. So you can write the equation. You can write the equation. Maybe you can use 2-point form. You have the point 0 comma 2 and then 4 comma 0. So what line is this? You have y equals negative 2 over 4 times x minus 4. So this is negative 1/2 x plus 2. Okay, is this correct? Yeah. So when x equals 0, you have y equals 2. So you have this. And then when your x equals 4, you have negative 1/2 of 4. That's negative 2 plus 2. That's equal to 0. And you have this. So you have this L3. So this L3, it has equation y equals negative 1/2 x plus 2. Okay. So again, let's study each line. For L1, you have y equals 0. So define G1 of x. That's your f of x comma 0. And that's simply x squared. And then this function G1 of x or g of x attains its extremum when g prime of x, which is equal to 2x, equals 0. So this means the extremum occurs when x equals 0. And therefore, you have the point 0, comma 0. Okay? And also, at the other endpoint, okay? At the other endpoint in here, you can evaluate. You can evaluate at 4. So you got this point here, okay? And then you got this other endpoint. Take note, this function here, it's just a function of one variable. So you go back to the methods in functions of one variable. Therefore, you need the other endpoint, x equals 4, so you have this. Okay? So looking at this function only, at this point, you actually get a minimum. Correct? Because at the point 0, comma 0, this guy here, f of 0, comma 0, that's equal to 0. On the other hand, using this, the endpoint 4, comma 0, at x equals 4, the function is 16. So the value of this function is 16. Okay? Next, for the line 2 here, you have x equals 0. You can define g sub 2 of y equals f of 0y, which is just 2y. So again, this is just a function of one variable. Methods we know from there can be used. So you can get, or the extrema of the function g can be obtained at the endpoint 0, comma 0, and 0, comma 2. So at this point and at this point. So similar, okay, to the previous one. And similar to how you do it in function of one variable. So again, at 0, comma 0, you got here 0. At 0, comma 2, you'll just get the value of f to be 4. Okay? At this point, the value of f it's 16. At this point, the value of f is just 4. So definitely this won't give you the absolute maximum or the absolute minimum. Not the absolute minimum because we have 0 here. Okay? And then on the line, you have this. Okay? You have this equation, y equals 4 minus x over 2. That's the same equation that I wrote earlier. So you define your g sub 3 by this. So you substitute your y on the y's in here. And then if you simplify, you'll just get 2x squared minus 5x plus 4. And then we can look at the extrema of this function here, right? G sub 3. And its extremum can be obtained, okay, when the derivative of this is equal to 0. So g prime of x equals 0. But g prime of x, that's your 4x minus 5. And 4x minus 5 equals 0. This will give you 5/4 over 11/8, meaning your x is equal to 5/4. That's 1 1/4. So 1 1/4, it's somewhere here, and then the y coordinate will be somewhere here. Should be lying on the line. Okay? So what did we get? We have the critical points. Okay? So we have the critical points and the possible absolute extrema at these points. You have your 1, 1, which you obtained using gradients. Okay? We have the 0, 0, and then this 4, 0 from line L1. We also have 0, 0, and 0, 2 from line L2. And then finally, we have the 5/4 over 5/4, 11/8. So you have these points. Okay? So there's a question, paano nakuha yung 11/8? Let us go back to this. So you got your 5/4. You substitute this 5/4 in this equation. No, in which equation here? In this equation here, the value of y. Okay? Let's see. So y equals 4 minus 5/4/2. So this is 16 minus 5/4 all over 2, and that's your 11/8. So dapat nasa line yon. Kaya dun mo siya isa-substitute sa line, not on this. Because this g sub 3, this is your function f. Okay, this is your function f. Okay. So, again, what's left to do here is to substitute these ordered pairs dito sa function na to. And whatever the highest value is, that's the absolute maximum. And whatever the lowest value is, that's the absolute minimum. So we do all the calculation. And as you can see, this is your highest value and this is your lowest value. Okay, so the highest value occurs at the point 4, 0. The lowest value occurs at the point 0, 0. So f has a maximum value of 16 at 4, 0, and a minimum value of 0 at 0, 0.